All right. So we're going to hop back into the code that we were writing for quicksort here momentarily. But I want to have a couple of announcements first. First is that we have an assignment due tonight. It's a tough one. So let me know if I can be of assistance. I'll have office hours right after class for an hour and also between 1 and 2. I actually finally don't have anything to do between my usual 1 and 2. So I can handle questions then too if you're still around. Expect a new assignment today. That will be the next thing that I am doing once I am available, is to make sure that you have a new assignment to work on. So we've covered quite a bit of material since the start of the last assignment, and we should probably be getting some practice with that ahead of the next exam. Finally, there is one person left to take the exam, so I can't hand them back today. However, if you took the exam on Friday, they are graded and I can at least share a score with you. So if you're interested in an exam score, come see me in my office. I can't give you the exam because one person is yet to take it, but I can at least tell you your current score before any arguments or changes.
What was the average?
I have not yet calculated the average, but I think it was pretty good. I think it was okay.
Better than the first, okay, or like I'm saying?
Tough to say. There are kind of outliers on both sides that may significantly affect. Since I kind of hone in on the median, the mean may be a bit different from that, but the median was good.
Stop asking me difficult questions.
It's a fair question. It's a fair question. I'll have a lot more once we're ready to go over it. I'll have calculated the stats and make sure that you will know where you place. Yeah. Very exciting is happening there. Someone is not in data structures. So let's go ahead and get started trying to finish off this partition before we hop into the next topic. So I think I made a couple changes since we did this. I think I had a slightly incorrect while here as we were getting started. So to give you a recap of where we are, quicksort is made up of a couple components. We need to figure out where we're going to be partitioning the array. So we're going to have everything larger than the pivot to the right of the pivot, everything that is smaller to the pivot to the left of the pivot. So the job of partition is to figure out where is that pivot. What is the pivot index or the partition index, where we're going to pass in the left part of the array and the right part of the array into two recursive calls to quicksort to sort the left half and the right half. So that is the job of partition, is to make sure that we return the index. And when we do return the index of the partition, that everything to the left of that is less than the pivot, everything to the right of that is greater than the pivot, and the array at that partition index is the pivot. So we started by saying we're going to choose the pivot to be the last element in the array. So we're passing in, from this example, we have an array of length 5. We're going to pass in 0 as the low index and 4 as the high index. So it's between 0 and 4. Somewhere in there, there's going to be a partition index. If we use this as an example, I just wanted to have an example to go through people with. We're going to choose 4 as the pivot. Question?
For the first quicksort, it should be position index -1.
Yeah, very much should be. This should be -1. Changed that this morning. Thank you for catching that. That would have been a pain to go test it. Probably what I initially had. My computer had to restart, so I had to re-implement everything from scratch. So that's how the typo appeared.
I think it would be spit.
9 or 10.
Yeah, because we're going to from low index to partition index -1 and from partition index +1. You're absolutely right. Good call. From +1 to high. It happens to all of us. I want to normalize that. That happens to all of us. So we're going to be choosing this 4 as our pivot value. So we need to make sure that everything greater than 4 is to the right of 4, and everything that is less than 4 is to the left of 4, and then 4 should be in its appropriate place. This is 1, 2, 3, 4, 5. did that on purpose. We know that 4 should eventually end up in index 3. Or at index 3. So it should eventually end up here with 5 to the right of it and 1, 2, 3 left of it. So that's what we want to make sure we are doing inside of partition. Then we're going to return the index of the partition, which in this case is 3, so that when we quicksort, we will go between 0 and 2, and 4 and 4. And that creates our 2 partitions that we're going to recursively call this on. Questions on where we are in the code, what we have left to do? So we said the pivot is the last element. That's for this first case going to be the 4. We're going to set an I and a j. The I is going to be low index, which is in this case going to start out at 0, and j is going to be high index -1. And the goal is going to be to find 2 numbers that are out of place. So I is going to continue to bump up until it finds something that is greater than or equal to the pivot. And j is going to bump down until it finds something that is less than the pivot. Once we identify both of those, we're going to swap them. And we're going to continue doing this process until we get a crossover. I crosses over j, and now I is greater than j. So while I is less than j, is how we want to start this. What's next? What do we want to do? I think the while will handle that. If this condition is false, then I is greater than or equal to j. The pivot, yeah. So we need to identify the ones that are out of place. So we can query these as separate while loops inside of this while loop. We just want to check the value of I, and we want to continue to bump that up until we find something out of place. So we can say while r of I is less than or equal to the pivot, and I is still less than j. Because we may very well find that in the middle of this loop, we just continue to bump up, and then we, yeah. So we can stop this early if I does not become less than j. Then we want to bump up I. Once this is false, then we know we have identified something that needs to be swapped on the left side. We're going to do the same thing on the right side. We will say while the array at j is now greater than or equal to the pivot, and I is still less than j. Then we want to bump down j. Once we have finished this process, we want to swap whatever is at I, array of I, and whatever is at array of j. So the question is, do we want to do a swap or do we want to make a swap method? We're going to end up doing 2 swaps here. So why not? Now that it's time to swap, I'm going to leave myself a to-do. Has anyone seen a to-do before? If you're in any IDE and you leave a comment that starts with capital to do, it creates this little item here on the left bar, as well as something that you can just kind of visualize. And this allows you to know places that you have stopped to come back to. So we know that we need to do a swap here. And if my goal now as I'm writing this is, oh, I need to write, I'm thinking that there's going to be multiple places in this that we might need to swap some things. We can write a swap method, and rather than continuing with this, we just kind of make sure we come back to this and eventually write it. So let's write a quick swap. Goal of this swap is to swap the I index of R with the J index of R. So we can make an int temp, that is Ri, then we want to overwrite that, Ri gets Rj, and then finally Rj gets. And then we just need to pass in the indices that we want to swap. So now we can go back to our to-do and actually call this swap. So we say, let's swap. We're gonna pass in the array. We're going to pass in I, because that is the index of what we want to swap, and J, which is the index of what we want to swap. I tried to use the same terminology between both of these so that it had linked up, but you don't necessarily have to use I and J. You could have first and second, you could have, that doesn't really matter if you use. All right, so that's the swap. We need a little bit more logic once we're done with this loop. Why? So this is everything that goes inside of this loop. What's left to do? We definitely need a return statement somewhere, but we're not quite done with our logic. We've swapped everything that is lower than the pivot with everything that is higher than the pivot in the array, and eventually this statement is false. I is no longer less than J. What's the last element of the array?
You gotta put the pivot in.
Yeah, we don't have the pivot in place yet. So we need to make sure that we swap the pivot into place. So there's a conditional here because the pivot may actually be where it needs to be. So we want to try to find the logic that's going to separate the case of the pivot's already in place with the pivot is not in place. So we're going to say if the array of I now is greater than the array where the pivot is, which is I index, then we want to swap them. This is the case where we want to swap. So wherever the low pointer is it's stepping up the array. Now we want to make sure that if this is greater than the pivot, then the pivot goes there. If it's not greater than that, then the pivot was already the highest value and it's already in place. Does that make sense? So if this is the case, then we want one last swap. We still want to swap in this array, but what are we passing to swap? What is I and what is J? That we're passing into swap. Yeah, we want I and we want I index. So I is the position that we bumped up, that is the thing that is higher than the I index, and we want to swap now. We want the pivot that is at high index, array of high index, into place, and its place is now the low value. This is kind of similar to yesterday on the board. I drew this out, we swapped it with the low pointer. Now this is going to swap it into place at the low pointer value.
Kind of just like a refresher, what if you put pivot in the swap instead of high index, what would happen?
Yeah, since we already did this could totally be pivot.
No, I meant like in the actual swap method. Would that be?
Oh, here pivot,
Yeah, if you put pivot, would that?
because this is an index, J needs to be an index, so we're gonna take the value, the data of pivot. And try to use that as an index into the array, which will quite possibly create an array set of bound exception. Where you could replace this with pivot is right here, since we said this pivot, and then I did not use it right here, so we should change this to pivot for clarity's sake. Now that we've done the swap, if and only if we need to, we're ready to return. What do we return? Remember that partition needs to return the index of what is in place, so the index of the pivot. What is the new index of the pivot? 5. Of course, I have an exception of some kind. Somehow we're passing in a high index of -1. I'll get this figured out. This is very, very, very close to right. But I will get this figured out and I will share with you tomorrow what the small bug is. But the logic here should be very, very close to correct. Probably have some kind of off by 1 years. Really want to work on it now, but I should not. All right, questions about the general logic? I already knew it. We only want to do these sorts if there's a difference of at least 1. Oh, not printed anything out, except that I tried to. Again, I'll get it figured out. Questions before we move on to the next topic? Yeah, I'll post this code and I'll come back and talk about it in sort of next class too. All right. Time to introduce our next big structure. This is one of the big main topics in this course. And it's incredibly important moving forward in computer science because trees are one of the most widely used, most widely studied structures. So they're very important to have an intuitive understanding of. Kind of self-motivating. You will use these a lot, starting now, and who knows when you will stop. So the reason we wait a little bit in this class to introduce trees is just about everything to do with trees uses recursion of some sort. Because a subtree of a tree is another tree. You can think of this like if you were to take the trunk of a tree and at some point look at the biggest branch on that tree, chop off that branch and plant it. What you would have is a smaller tree. And you can continue to do that process over and over and over again. A trunk is just a really large branch. So let's motivate this with a fun game that I played with a couple of you in my office hours. But we're going to guess a number between 1 and some upper bound n. And for every guess, I am going to tell you whether you are too high, too low, or right on. So the question I have for you is how many guesses does it take in order to correctly identify a number between 1 and 1,000? If you are guessing optimally. Yeah. You can use basically binary search for this. You're gonna guess in the middle. And then regardless of what I tell you, you're gonna shape the size of the guess domain in half. If I say it's less than 500, you're gonna know that, well, you're playing now a new guessing game between 1 and 499. You restarted the guessing game with a smaller game. If it's between, if I say it's greater than 500, then you know it's between 501 and 1,000. So it's just an offset of the other game by 500 numbers. If you would have guessed 1, now you guessed 501 before, and it's just offset of the other game. So you have a new game of size 500 regardless of the result. And the next time you have a game of size 250, and the next game you have a game of size 125. And you figure out how many times you have to cut this in half before I end up with a size of 1. If we wanted a way of visualizing this, I'm going to use a smaller example than 1,000, but it scales up to that size. We need to replace these soon, we're running out of ink. But we're going to play a game between 1 and 8 rather than 1 and 1,000. Because powers of 2 are beautiful things. Well, at least this gives you between 1 and 7. It's always a power of 2 minus 1, but this tells you where the middle is. If you were to draw this as an array between 1 and 7. Starting at this node at the top of this tree structure would tell you where the middle of this array is, and it's the first number that you should guess. If I say that it is less than 4, you want to take the left side of this is a new tree, and you want to guess this number, which is if you take this, it is the new middle of this substructure. If I say that it's greater than 4, then you have this, and you want to say the middle of this substructure. Regardless of whether you're at 2 or you're at 6, let's say we're at 2, if I say it's less than, you know exactly what the number is on the third try. We know that it's of this substructure, it's the middle of that. If I say it's greater than 2, we know it's right there. If it's less than 6, we went down here, then we know it's exactly 5. And if it's greater than 6, we know it's exactly 7. So in 3 guesses, we've hit all of these possibilities. We know within 3 guesses, we can get the number. One thing to note is that this entire game is a sub-game of the game between 1 and 15. If this were a tree, this would just be the left subtree of a game where the right subtree of this is everything between 8 and 15 and just mirrors exactly this. So this is again a way to visualize the logarithmic scaling of tree structures. Every time that you move from one tree to a subtree, you're just removing half of the structure. With one more guess, we go from 3 guesses to 4 guesses, we can guess a number that's twice as big. Or a range that's twice as big. So that's kind of the motivation, and we see this a lot in computer science applications, where we end up with a structure that we want to traverse that looks like this. Questions on this? So the answer from 1 to 1,000 is 10 guesses. 1 to 1 million, 20 guesses. 1 to a billion, 30 guesses. Which tells you, since there are fewer, I guess there are, what, 8 billion people in the world approximately? To get from 1 billion to 8 billion to 4, 8, it's an additional 3 guesses. So with 33 guesses, you could take the entire world, and if you could find some question, some way to carve that population exactly in half, 33 times, you could identify down to the individual some way. You could pick out an individual for the entire population of the world in 33 guesses. Which is kind of cool to think about, but you're basically guessing a number between 1 and 8 billion. And that would take you approximately 33 guesses. Not quite, because 2 to the 10 is 1,024, not 1,000. So extremely efficient structures. But note that natural recursion where we say, we have a tree, we go down the left branch of that tree, or the left edge of that tree, we end up with another tree structure that's about half the size. That's naturally recursive. So everything we've talked about to date has been some kind of linear structure. An array list is a linear structure, a linked list is a linear structure. A stack and queue use an underlying list, so there are naturally linear structures. There are multiple structures in computer science that are non-linear structures, and this is the first one that does not adhere to that. And the more complicated structures are all non-linear. One way to intuitively think about it is linear structures have this concept of the index that comes before or the index that comes after. So there's kind of a before and after, a natural timeline of moving down the array. Instead, we're going to have a hierarchical structure with a tree where we have levels. And we have left children and right children and parents and ancestors and descendants and all sorts of really strange terminology that we can use to describe relationships within this structure. So we're going to go through a lot of these terms that we're going to use. And in case you need a little more time here, the terms that you're going to see are, there are quite a few of them, but a lot of them make sense given things like lineage. It uses the same terminology that we use when talking about a family tree, because a family tree is a tree. So we derive a lot of our terms from that concept. The other half come from graphs that we will talk about hopefully by the end of the class. All right, so the root is the initial node, the base of the tree. When we had this tree of 1 through 7, it was the 4. The place that you start, the root of the tree. If you're thinking of an actual tree, it would be the value of the stump before you start. We have a parent for every node except for the root. The node as you were to go, if you're to traverse up the tree, closer to the root, it is the node that is directly above it. So we have the tree that looked a little bit like this. The parent of this node is that node. It's one level closer to the root. And notice that for any node, there's only one of those. Unlike with us humans, we have 2 parents. Every node has a single parent, regardless of the branching factor of this tree. Note that I'm drawing binary trees here, but there's nothing that says we can't have more stuff. Regardless, we're only allowed to have a single parent. We can't have some connection like this. As soon as we make that connection, it's a graph, not a tree. So one of the rules of trees, each node can have at most one parent. All nodes have one parent except for the root. Children are nodes that are one level deeper into the tree, and a node can have an arbitrary number of children. If you're at the very bottom layer, you may not have any children. A node may not have any children. But there's no limit. You may have, a node may have one child, a node may have 10 children. We don't know how many children a node is going to have. It just has between 0 and an arbitrary number. We can define siblings as nodes who share a parent. Very similar to a family tree. We can define the key as the value that is stored in a tree node. So like a linked list data or a linked list value, we have something that is stored at that particular node in a tree. This could be an integer like we had with our 1 through 7. Each node stored an integer. They can store arbitrary things. They can store objects. They can store integers. It doesn't really matter. Just like with other structures, we make this generic so that we can instantiate a tree structure with any arbitrary structure. We can define an internal node as any node that's not the root. So the root is the only non-internal. We can recursively define a tree in terms of a subtree. A subtree is just a recursive definition of a tree. So there is a new root that is an internal node of the original tree. And that becomes the root of its subtree. So again, we have, I probably just left this up there. If we were to kind of talk about the left child of this node, that's saying move down the kind of left pointer here, we end up with a subtree with a new root. So we can recursively define a tree in terms of a subtree of an existing tree.
Children and parents.
Correct.
But if you have, like, let's say that one parent has 3 children, then the rest of the tree has all the same structure.
Not necessarily. So there are different kinds of trees that have certain rules associated with them. Like a binary tree says that every node has at most 2 children. But you will find that there are different kinds of tree structures that do different kinds of things that require different associated rules. For now, we're just talking about them in general, but we will hone in on especially binary trees as what can we do with them. Next, a leaf node is a node that has no children. So you've reached kind of the end of the branching structure. You can't branch any further. We're halfway there. There are a lot of terms associated with trees. It's kind of overwhelming. An edge is what we call the connection from one node to another. When we don't want to further specify what kind of connection. Like you could have this particular node's parent defines an edge between a node and another node. A child defines an edge between a node and another node, but in general, we just use the terminology edge to define the connectors between nodes. Finally, we can define the tree and talk about some terms about the tree as a whole. So the height of a tree is the largest number of edges between the root and the leaf that is farthest from the root. So the maximum number of edges that you need to traverse to get to another node from the root. That means if you have a tree that is just a root, it has height 0. If you have a root with a connection to a single node, that tree has height 1. So the tree structure as a whole has a height. Each node has an associated depth. The depth of a node is the number of edges that you need to traverse from the root to reach that node. So the height is defined for an entire structure, the depth is defined on a node by node basis. The level of a tree is the mathematical set of nodes that are contained at that depth. So level 0 of a tree contains just the root. Level 1 contains all of the children of the root. Level 2 contains all of the children of the root, etc. Finally, we can define ancestors. Node A is an ancestor of node B. If you can start at node B, traverse towards the root by going parent, 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 and eventually see node A via some number of querying parent. Likewise, a descendant. Node B is a descendant of node A. If you start at node A and you query all of your children, all of your children's children, all of your children's children's children, eventually you reveal that node, the query node. So just like a family tree, ancestor goes back in time, ancestor in the tree structure goes toward the root. Descendant, some children's children's children, you go back toward the leaves. The last definition that I tried to show a little bit visually here is that a tree is no longer a tree if it has any cycle. A cycle is just a way to get from a node back to itself by traversing a set of edges. So if we had a way to get from a node to itself by querying child, 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 not a tree. Or parent, 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 we have a way to get back to where we started, not a tree. Just like it would be really weird if your great, 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 great grandparent was yourself. Something is horribly wrong if that's the case. We've broken time, we've invented time travel, and something is very wrong. So here's a way to visually kind of represent and show each of these terms in terms of a tree. So we have a root. Every node stores a key, which is what we're going to call our data. We can have a node's data in a link this, we're going to call it a key in a structure. If we have a subtree, so this is a subtree of the entire tree, then we can have a parent-child relationship. So here's the parent, here's the child. These two children are siblings because they share the same parent. We have a set of leaf nodes, but note that the leaf nodes don't necessarily all have to be at the same level. We define each of these levels as the set of nodes that are at that level, the number of edges between the root and that. So what's in common between D and E and G and F is that it takes 2 edges to traverse from the root to reach any of those nodes. And then we just call these connections between nodes edges. So lots of terms, lots to become familiar with. Any questions about the tree object and the terms for a tree object? Yeah,
What do we call it, key versus data or element or whatever?
it ends up being a key because the tree can be, so a tree can represent a set. It's one of those underlying structures, both a hash and a set. Sorry, a hash and a tree can be used for that. And so the reason it's called a key is eventually you get what's called a map. And we're gonna talk about maps later. So basically you have a set of queries. And then for each one of these queries, you have an associated list of values or a single value that becomes the lookup. You can think of this kind of like a dictionary. Here we have a word. Doesn't matter what it is. And here we have a list of definitions for that word. This is a set object. And this is a list of some kind. So this entire structure is called a map. You map this query to this list. So this is what we call the keys. So in general, this is just used in tree terminology because it's used in the same way in map terminology.
Okay.
A great question, though. It seems arbitrary and confusing at first. But there's different names for each of these concepts that are exactly the same. So let's actually talk about how we're going to store one of these tree nodes. So what should be there? We have a tree node of type T. So what are the elements? What are the fields of one of these nodes? Yeah, we need some kind of key. We can call it data, we can call it a key, we can access it by .key, .data. That doesn't actually really matter how it's done internally. So we have some data field of some kind. What else do we need to store?
Do we need like a next sort of, like, move it?
Yeah, so we need some way of, so a linked list had a next because a linked node pointed to another linked node. How many tree nodes can a tree node point to?
So,
If it's a binary tree, yes.
yes, and
Yeah, we don't know, so we're gonna have to store it as an array. What else? This one is optional, so this is everything you need for some circumstances. For other circumstances, you may want to store one more piece of information.
Means I can actually move them.
We have the parent. So yeah, this would be methods. If you want to do things like move from one to the next, you just look at the reference, the pointer at what is this child? Where is this child? And that will be another node structure. So you can pop between them by just querying, what are you pointing at? Go there. What are you pointing at? Go there.
So we always need something like current that's moving and pointing.
Yeah. Yeah, you'll have some kind of current, just like you do in a linked list structure, except a tree, instead of having a linear. This to that, to the other thing, to the next thing, we're gonna have a large branching structure. From an initial point. So it's very much like a linked list, except a linked list is one dimensional and a tree is kind of a cone.
When you make a tree though, there'll be like a pointer there like head, right? So it won't be nothing that it's on a standalone right?
Yeah. We'll talk about exactly what a tree needs, because a tree is gonna need things like a root, and we need to identify where do we start. So methods of a tree node, we need basically just getters and setters for all these fields. We need the ability to get the data, set the data, or the key. To get the list of children. So that we can do something to that. And the same thing for parents. Maybe we want to be able to set the children and set the parents, maybe we don't. That'll again be application dependent, dependent if we need to construct the tree structure. In which case you may need to do that. You may want to limit this to only at construction. When you make a node, you make the associated links and then you can't change those links. So in that case, we would only want to do it at construction time. Last of the tree object. So this tree is just a number of tree nodes. Well, it really is just a link, it's a pointer to the root, and then the root has associated children with it. So the tree, just kind of like the linked list, kept track of the head, and then the head keeps track of the next node, which keeps track of the next node, which keeps track of the next node. The actual linked list structure doesn't keep track of all of those nodes. It just keeps track of where it starts. The tree just keeps track of the root, where it starts, and lets the root's children tell us where we can go from the root. And those children's children for where we can go from there. So the fields we need a root. It may be worthwhile to store a size or a height. But it's not necessary in all circumstances. So all I have here is the root, but there may be times where you want to store things like.
What would be a situation where we need to do that?
So. Let's see, that's a great question. If we are. Trying to figure out something like the maximum number of nodes that we need to traverse between a root. For the sake of complexity, or to determine, for instance, whether or not a tree is balanced. There we go, that's the algorithmic one. So we can have two different similar tree structures. I will give you something from algorithms because it's reasonably important. We talked about how we could store the numbers between 1 and 7 in this associated structure. There's another way we could do it. We could do this. This is just a linked list. Which one do you think is more effective? When we talk about things like how do we insert into a tree, into a binary tree, how do we delete from a binary tree? We want some way to end up with this structure if we want the numbers to be in order. So that we can search it. And not this order. So in algorithms, you will learn about how when you're inserting, depending on the order of insertion, you don't get this guarantee. You might end up inserting in a way that makes something that looks more like a linked list than looks like a tree. So because of this, we need some way during the insertion process to convert the fact that we are making this into this. So that we get that nice logarithmic guarantee.
Part of that, I think, is not correlated, like if you delete 2, how do you assign priority between 1 and 3, the command of 4?
Yeah, so you can either bring up the 1 or you can bring up the 3. And it becomes much more complicated in certain circumstances because there might be subtrees down here in certain circumstances. And if you just bring up the 1, what happens to this entire subtree? If you bring up the 3, what happens to this entire subtree? So the rules get kind of complicated for that. But it's something that's very much worth studying because the entire purpose of trees is to take this linear time or this linear. If we queried 7, it would take 6 edge traversals to get there. Whereas to query anything in here, it's max 3. So this gives you that logarithm guarantee. And so we need some way to guarantee that we can't produce this structure, we have to be able to produce that structure. So that's algorithm's task, to figure out how to balance a tree. But That's coming in your future. We are out of time. We'll come back and finish this off tomorrow. Binary trees are fun. Office hours starting now. Anybody would like to do the homework?
Oh, goodness.